I'm Derek from the University of Southampton.
I'll wait that you've got 5 minutes to go.
Okay. We're starting a bit late, I note. Okay, thanks very much. I'd like to thank the organisers for inviting me, Felix and the other organisers. Great delight to come here. And thanks for organising the college dinner last night. And I hope everybody had great revelry times afterwards and that you're all fit for today. Before I start, I want to say that for most of my career I've been a paleoecologist. I've been studying Holocene environmental change, mainly looking at the impacts of climate on vegetation responses and to some extent how human activities have engaged with that. And the one thing about being a paleoenvironmentalist is that you do take a long time scale perspective on things, and that was how I was looking at the world up until about 10 years ago, when I got involved in projects that really required a shorter term perspective, because it was about looking at degraded environments, areas where there are particular difficulties between the human and the environment interactions. So what I want to talk about today is how we've kind of brought some of those paleo methods into play for looking really at modern environments, modern concerns. Let me see if I can get this working. Is that the right way? Yes. So I really have, over the last few years, become interested in trying to identify complex dynamics and study complex dynamics which are set up by particularly mathematical modelers and physicists within real data sets from real systems. So really trying to disentangle cause and effect drivers and responses, looking at trade-offs in observed time, path-dependent trajectories, trying to get some sense of the different speeds or the rates of change of processes, rates of slow change, this idea of creeping normalcy, which I'll talk about later, tipping points, critical transitions, feedback mechanisms, looking at time lags, hysteresis, and bringing those into two areas which we've developed, and that is setting safe and just operating spaces and trying most recently to simulate some of these complex behaviours as tools for decision making. So the kind of research questions that we've been looking at over the last few years have been quite simple ones, really. So how does the complex social ecological system that we see today, how does it actually function? Can we say something sensible about looking at the recent past as to how the systems actually function? And by looking at those functions, do we get any sense of where there might be leverage points for managers today to perhaps offset some of the problems? Can we simulate possible futures that capture that complexity that we've observed? Can we identify within those simulations dangerous trajectories which we perhaps should avoid? And then consider the policies that would maintain those non-dangerous spaces, those safe spaces. And what I want to do is to do it by case study, just 3 case studies that we've worked on, just to kind of, I don't have any generalizations to give you, they're really just demonstrations of how we might use some of these ideas of complexity along with real data sets, particularly time series, to give us more insight. And these are 3 examples that we've been looking at recently in developing world context, 2 in China, that's the Lower Yangtze one, also Lake Erhai, which is in the west of China, and the Chilaka Lagoon fishery in India. So I'm just going to go through each of those in turn. So in the Lower Yangtze, this area here, you can see the Yangtze coming out into the China Sea on the over here. Here's Shanghai, here's Nanjing, and it's this whole area of the Lower Yangtze where we see a lot of environmental change over the last 50 years. There are issues still of really catastrophic flooding. There's issues of water quality. There's soil degradation. There's changes at the coastline, particularly with infrastructure projects like dam building. And then there's the urbanization context in this area, massive economic development, with infrastructure like the Three Gorges Dam upstream. There are demographic changes, the population is still expanding, and yet in the rural areas it's becoming, there's a lot of depopulation and a lot of ageing. So there's a lot of complex interaction potential there between society and the environment. What we wanted to do was to look at some of these interactions by taking long-term indices of provisioning and regulating services, basically production of agriculture, and some of the indicators of environmental quality. And this is really summarising a lot of information that we've got from the area. You've got 4 panels here which have green and red curves on, and the red curves are basically taking a great number of time series for 5 different areas, well 4 areas and one aggregated one, which show over a period of the late 20th century, early 21st century, the rise in productivity. So if we look at the red lines, we're looking inside that index, we're looking at timber production, crop production, pig production. It's an index that shows there's been massive increase in productivity, certainly since the start of modern China in 1950. The green line is the more challenging one to obtain, because that's the index of environmental quality, which, as you can see in each of the panels, is going down over time. And in that green index, we've got data from essentially lake sediments. This is where we bring in the paleoecology, which gives us some time series of water quality, of soil erosion. We also have indicators of air pollution, which we can add into that index. So it's a very high level summary of the state of the environment, essentially, in the lower Yangtze. And it's a trade-off, it's a regional trade-off. It's one that's been accepted by farmers and policymakers now for many decades. But it's getting to the point where you're seeing feedbacks into the system from that poor environmental quality, not just in air quality. In air quality is an issue with health, but also there are issues of tipping points in downstream lakes and rivers, where eutrophication is now a massive problem. We can look at some of the we can begin to tease out some of the drivers of these change, which is essentially an evolutionary emergence property of the system, by just putting environmental degradation against economic growth. And and for 4 of these areas, we can see that if you plot environmental degradation against economic growth, you've essentially got these curves which are rising. As the system, as the environment, as the people have got wealthier, the environment has basically just become more and more degraded. And we actually find this in many other developing countries. You know, there's a development issue that is related to trashing the environment. And one of the big issues is how can you break that coupling between wealth creation and environmental degradation. You might be interested just to see what the same kind of data looks like for the UK. So just recently we published a paper in Science of the Total Environment, where we've amassed quite a lot of time series data for UK agriculture but also environmental quality. And in the pink you can see from the 1950s this rise in productivity. This is the wheat yield of the UK, rising to a peak and then flattening off. Livestock does a similar thing, but actually starts dropping. But the interesting data on this is really our amalgamation of data for environmental quality, which starts from late 1970s, and you can see it actually declines in those first 2 or 3 decades, very much like the Chinese example. But then, unlike China, we've got this kind of apparent recovery from the late 90s towards the present time. However, it's very difficult to really understand this coupling that's going on here, because biodiversity, as many of you will know, continues to get worse in the UK. If you take farmland birds as a proxy of agricultural linked biodiversity, and the effects of offshoring our degradation through imports, we're unable to evaluate within this context. But going back to China, what we have with that trade-off is a question of how you could reduce the coupling, how you could make the environmental regulation, the environmental quality to be not linked to the development. And we've used a framework here which I think was developed by Mark Brownsford and Terry Dawson, which we've used in a recent paper with Terry Dawson, as a framework for looking at the decision making within one of those localities in China. And what we can see by looking at focus groups and stakeholders and questionnaires with farmers is that there's really one quite simple positive feedback loop that's been going on for several decades, and that is that farmers have a desire to get wealthier and wealthier, and the gradual liberalisation of China has allowed them to do that. And they've been allowed to do that with actually very little concern about the environment. In fact, in terms of intervention by governance, it's been very mild. It's that minor loop where the government has actually just had interventions through short-term fixings of crop pricing, for instance. When they saw that the yields were going down in one area, they just shifted prices in order to encourage farmers to change their choice of crop. But in fact, there's been very little governance intervention in terms of the environment itself, and that's really what's lacking, that policy that would either regulate or incentivise farmers to have a stronger stewardship of the environment. So before we're getting some way to being able to tease out the mechanisms of the decision making that underlie this kind of long-term dynamic of trade-off between society and the environment. Conflated with that problem of the lack of environmental regulation is, in fact, within this county we're able to look at the farmers' perception of environmental degradation and just ask them, when do you think the environment began to degrade? So take water quality. When do you think the water quality started to get poor? And in fact, they all underestimate the time since the environmental quality started to degrade. So this is a classic example of creeping normalcy. We've got a slow process in terms of human lifespan that is actually undermining the resilience of the whole system. So we need environmental protection policies urgently, but in some cases it may be too late. And certainly with respect to lakes in China, about half the lakes in China now have reached a very poor quality water state. And I want to look at one in particular, Lake Erhai in Yunnan, the mountainous western side of China. This is a large lake, 50 kilometers long, a catchment of 2,000 square kilometers, much of it mountainous, but 2 million people living in this environment. So we have this kind of lake catchment social ecological framework. And the issues here are really the water quality of the lake. Go back to the late 90s, and we had a kind of low eutrophic state, pretty clear. You'd say it was a pristine environment, it had a very healthy fishery. And then around the early 2000s, we started to see algal blooms and floating macrophytes, not just occasionally, but almost continuously. And that's been the case right up until the present time. So one would argue that maybe there's been a critical transition at this point. And indeed, if one looks at the water quality monitoring data available from 1992 and plot it to the nutrient concentrations in the water, which we can argue is a reflection of nutrient loading to the lake, then we can see that there was a certain amount of insensitivity to that loading for the time up to about 2001, and then we see this rapid change to what you could argue is an alternate state for the lake in its eutrophic condition to about 2003. And then since 2003, although there's been some attempt to reduce nutrient loading through land use practices, you can see that there's been no recovery in water quality. And the key challenge, of course, is to raise the water quality back to its original status, some kind of restoration. And of course, this looks very much like a mathematical catastrophic bifurcation scheme. So we've been looking at this, and we've looked at a lot of paleo data and other time series data to try and understand the role of the environmental changes in determining this tipping point. You can see the tipping point at the top there, seen in the diatom records going back to 1880. Going back to 1880, you can see that we see these fairly constant values, and then quite a clear drop here, statistically significant drop around 2000, 2001. And looking at other data from the lake sediments and from census records, environmental records and climate records, you get the sense that there's no simple driver explaining this. It's a combination of nutrients. There's a temperature issue there. There happen to be warming and dry trends have taken place in the decades prior to this, and low water levels as well. What we hypothesized at the time was that as the nutrient loadings increased and the algal productivity was increasing, it developed, the lake developed anoxia in its bottom waters, which then which enabled a new positive feedback loop to be generated, feeding the lake from phosphorus that had been stored previously in the sediments. Since then, we've kind of reconstructed what those loops might have been with a causal loop diagram here, and we've kind of gone about testing the strength of these loops by looking at the quantitative correlations and stability analyses using the time series data. And effectively what we have is a loop 1 that was dominant up until about the late 90s, which was very much developed around macrophytes, and then around the late 90s another loop developed, which is indeed this anoxia driven loop which drives phosphorus recycling into the sediments. So there are opportunities now for the managers to think about restoring this lake in terms of levering that particular feedback mechanism. And so nutrient loading is particularly one that they've got to concentrate on, but it will also probably have to be with interventions in lake level and possibly even fish catches as well. And new modelling is really required to experiment with these combinations of factors in order to choose the right solution. Just to say something quickly about safe and just operating spaces, while we were doing this, we began to think about how one could take these time series and use them to define the current status of that environmental condition as being in a safe or dangerous condition. And we developed this in a paper in 2014. Here's looking at the actual tipping point in the water quality as an example of going from safe to red, green to red, but we've done it for other environmental conditions as well, such that you can produce a diagram like this, which kind of mimics the planetary boundaries diagram, so that we can have sectors around this circle of safe, cautious, and dangerous conditions. Here, water quality and upland soil stability are the two really that are in particularly precarious states, whereas the regulation of water and some aspects of air quality are kind of worrying but not in that dangerous state. And there's a social issue there as well. We can put in the conditions, the norms for society at the moment, so we can see here that that water, availability of fresh water is one of the worst aspects of societal norms at the moment. This will be where 100% of people have good piped water, and so half the population still have not got access to that. And so it's a snapshot really of social conditions and environmental conditions for managers. But of course the problem of this kind of planetary boundaries diagram is that we're looking at different variables and we're treating them very much as kind of single operating variables, whereas in fact, of course, in reality they're interacting. So the final example I want to just mention quickly is this one in India, where we've tried to take a much stronger multi-dimensional view of the problem. And the problem is that Chilicaloon, I think it's South Asia's largest fishery on the western side of the Bay of Bengal. It has already gone through a collapse of its fisheries in the 70s and 80s. And at the present time, the concern is about the switch in technology that's taking place amongst the fishermen, that many of them are moving from this traditional form of fishing, fairly low tech, to one where they're clubbing together and buying motorised boats. And it's a big fishery. The fishery is actually supporting about 40,000 fishermen, and the wider population that's dependent on that is about 250,000 people. So the questions for the managers of this water body is very much about how it should be managed now in order to maintain a catch yield, a fish catch yield, which is sustainable well into the future. And so what I want to talk about is simulating some of those future changes. And this is work by Greg Cooper, who I was fortunate enough to supervise in his PhD. And we've just recently published this paper again in Science of the Total Environment. And Greg set about this using a systems dynamic kind of model. There's process modeling inside here as well. So it's a bit of a hybrid, I guess. But it includes all the drivers that were decided by the stakeholders, the managers, and it includes at least 4 major feedback loops. He was able to validate against historical data from the 1970s. So here you can see in black dots and in black lines, these are the observed data. This is for salinity, top left, macrophyte coverage, total fish catch, and this is catch per boat, of which the data were available. And you can see that the model does a reasonable job in showing these quite abrupt changes. This is the point of the collapse here, and even with errors in the sensitivity analysis, you can see that this does a really reasonable good job up to plus or minus 5% at least. So that gave some confidence that you could use this model to simulate futures based on different scenarios. And he chose 3 scenarios: a business as usual here, one where there would be some annual fishing bans at sensitive times of the year to control the catch of juvenile fish, and then a third scenario where there would be the fishing bans, but also a regulation, a cap on the number of motorboats. Oh dear. And you can see these 1,000 forward trajectories, and the system clearly can collapse within the model, and that's where you get the red coloration showing that these would be dangerous trajectories to follow. And you can see in the pie charts the balance between the safe in green, the cautious in yellow, orange, and the dangerous in red. And clearly, as you have more bans and more regulation, then there's a greater chance that you stay within a safe space. But actually giving that to stakeholders, to managers, is not straightforward at all. It doesn't provide them with really the clear-cut choices that they would like to make. And partly that's because there are too many levers for them to manage. They could start thinking about fishing bans, they can start thinking about motorboats, but they can also start to manipulate the outflow to the sea. They can begin to think about the flows of water coming into the lagoon. And so it really needs a kind of multi-dimensional tool. And so Greg worked out what I think is quite a useful tool for this. In other words, he tried to work out the probabilities of all of the main drivers that would be could be selected simultaneously. And so in these panels for business as usual, for the fishing bans and for the fishing plus boats, we've got basically probability plots here which show the percentage of outcomes for each driver that stays within the green or the safe space. And here for, by contrast, is the percentage that end up in dangerous space. And so that you can basically say that if you can remain within this green part here, and in that green part there, and in that green part there, and in the green part there, and that one, then you've got a greater than 75% chance of actually maintaining a sustainable fish yield out through several decades. So that's a kind of fairly novel approach, I think. We haven't seen it before, and we're now beginning to take that to the stakeholders to see whether they appreciate that as a tool that they could use. So just to wind up, I've just really got a couple of summary points. I think that where we've been looking at landscape systems and using these approaches, we see the world as a very complex place, and the dynamics between people and the environment are invariably difficult to tease out. And what I've been showing you here are just some of the ways that we've been trying to do that in order to try and bring more certainty to decision making. So systems theory, I think, is the framework, has certainly helped us. Multiple time series from all sources, creating simple causal loops, hypothesizing about feedbacks that could be there, and then going out and trying to test them, we think is useful, and then constructing simulation models that can actually collapse the systems, so that we can be quite modest, I think, in offering the suggestion to managers that perhaps all they really want to do at the end of the day is not make mistakes. They just don't want to go into the dangerous spaces, and that if they can just keep the world safe, that might be good enough. So thanks very much.